A computer is something you are likely staring at right now. Yet, if pressed to define its fundamental nature, not its function, but its essence, most people falter. This section explores the gap between our daily use of technology and our understanding of what a computer actually is. Consider a laptop keyboard as depicted in the visual sequence for Figure 1. This image represents the interface we interact with, but the light pulsing beneath the surface hints at a complexity that most users never see. We often define a computer by its utility. It runs programs, connects us to the internet, or processes data. However, as the source material suggests, that is like defining a human being as a machine that eats. To truly understand the what, we must look past the how. The problem lies in the ubiquity and diversity of modern computing. Look at Figure 2, which presents a split-screen comparison between an ancient abacus and a modern smartphone. Both devices perform calculations, yet they appear to have nothing in common. This paradox extends to our modern environment. Your alarm clock, the ECU in your car, traffic light controllers, and the servers delivering high-definition video are all computers. Despite their vastly different forms and functions, they share a singular profound identity. This commonality is what transforms a pile of silicon and metal into a system capable of simulating a universe or playing a symphony. The core question that drives this exploration is what specific property allows these diverse machines to be categorized under the same name. We see a common thread in Figure 3 where various devices like microwaves and smartwatches are tied together by a glowing pulse, leading to a central question mark. This visual represents the search for the universal architecture of computation. We are looking for the skeleton of the machine, the underlying structure that redefines what it means to compute. For a computer science student or an engineer, this definition is not just academic, it is the foundation of every system ever built. The answer is older than electricity and deeper than silicon. It is a conceptual framework that allows raw matter to be organized into a system of thought or logical processing. By the end of this journey, the screen you are looking at will no longer appear as a mere gadget, but as a physical manifestation of a logic that has been evolving for centuries. This is the starting point for TechMunk's deep dive into the soul of the machine. To understand the modern computer, we must trace its lineage back to a time before the word referred to a machine. In the 1800s, a computer was a professional job title, a person tasked with solving complex mathematical problems for hours on end. These human computers were essential for calculating tide tables and artillery trajectories, but they were limited by human fatigue and error. This limitation sparked a revolution: the desire to build a machine that never sleeps, never forgets, and never tires. Figure 4 illustrates the Jacquard loom, an early 19th century invention that used punched cards to control fabric patterns. This was a pivotal moment because it introduced the concept of a physical program, a set of instructions that a machine could read to perform a specific task. This idea of instruction-based machinery was expanded upon by Charles Babbage and Ada Lovelace. Babbage designed the difference engine, while Lovelace wrote what is considered the first algorithm, recognizing that such a machine could do more than just crunch numbers. It could process any information represented symbolically. Later, Alan Turing conceptualized a machine that could read and write symbols on a tape. This Turing machine, shown in the conceptual model of Figure 5, proved that a simple mechanism following basic rules could, in principle, perform any calculation that is mathematically possible. The narrative of computation reached a climax in 1945 with John von Neumann. He formalized the architecture that remains the blueprint for nearly every computer in existence today. Look at Figure 6, which shows the iconic diagram of the von Neumann architecture. This model was not just about the electronic circuits. It was a structural answer to the question of what a machine must possess to be considered a computer. It moved the field from specialized single-purpose hardware to general-purpose programmable systems. By separating the processing unit from the memory, von Neumann created a blank slate machine. This history teaches us that the computer is not an invention of the digital age, but the culmination of a centuries-old quest to automate logic. For a student of computer science, understanding this progression is vital because it highlights that hardware is merely the vessel for the logic defined by Turing and von Neumann. We are not just building faster circuits, we are refining a structural philosophy of information. The essence of a computer is defined by a specific four-part structure known as the von Neumann architecture. As shown in Figure 7, this structure consists of four interconnected boxes: input, memory, the processor, and output. These components work in harmony to transform raw data into meaningful information. The first component, input, is the interface between the physical world and the machine. This includes devices like keyboards, touchscreens, or sensors. As the visual in Figure 7 illustrates, the input's job is to convert physical signals, like the pressure of a finger or the sound of a voice, into a digital format the computer can manipulate. The second component is memory. This is a dual-purpose storage area that holds both the data to be processed and the instructions telling the machine what to do with that data. In modern terms, this is represented by RAM and long-term storage, but abstractly, it is any system capable of holding a state. The third component is the processor, often called the central processing unit or CPU. This is the brain where the actual transformation happens. It fetches instructions from memory and executes them. At the most fundamental level, the processor is a network of tiny switches called logic gates. Look at Figure 8, which demonstrates a logic gate animation. Specifically, an AND gate is shown. If both inputs are off, 0, the output is off. Only when both inputs are on, 1, does the output become on. By combining these simple operations, AND, OR, and NOT, the processor can perform complex arithmetic and logical comparisons. This leads to the final component, output. This is how the computer communicates the results back to the user, via a screen, a speaker, or even a robotic arm. The computer takes what are essentially meaningless patterns of electricity and translates them into pixels, sounds, or movements. Summarizing this process, input brings data in, memory holds it, the processor manipulates it using basic logic gates, and output presents it to the user. This architecture is universal. Whether you are editing a photo or running an AI model, the underlying process is a sequence of these four steps. The diagram in Figure 7 isn't just a technical map, it is the skeleton of digital thought. By understanding these four blocks, a student can see that even the most complex software is just a massive orchestration of simple switches being flipped according to the rules stored in memory. Beyond the physical architecture lies a deeper theoretical concept, Turing complete. As shown in the animation for Figure 9, a Turing machine uses a tape and a read-write head to manipulate symbols based on a table of rules. Alan Turing proved that any machine possessing the four components of the von Neumann architecture and the ability to follow rules is Turing complete. This means it can compute anything that is mathematically computable given enough time and memory. This is why a computer is a universal machine. It is not a fixed-purpose tool like a hammer. It is a blank slate that becomes whatever the program dictates. To see this in the real world, consider the example of a smartphone calculator as illustrated in the step-by-step journey of Figure 10. When you tap 2 plus 2, your touch is the input. The operating system stores these values and the addition command in memory. The processor then fetches the add instruction, executes it using its logic gates, and stores the result, 4, back in memory. Finally, that 4 is sent to the screen as output. This entire cycle happens in microseconds. On a larger scale, consider watching a video on YouTube. As shown in Figure 11, the input is a stream of binary packets from a server. Your phone's memory buffers these packets, while the processor performs billions of tiny mathematical operations per second to decode the compressed data into individual pixels. The output is the fluid motion you see on your display. The most mind-bending realization is that the computer has no inherent understanding of video or math. It is merely following meaningless patterns of on and off. It is the arrangement of these patterns, the program, that creates meaning. This explains why the same device can be a music studio one minute and a flight simulator the next. Because the underlying hardware is Turing complete, its potential is only limited by the instructions we provide. For developers and engineers, this is the ultimate payoff. You are working with a machine that can, in theory, simulate any other machine. As seen in Figure 12, people have even built Turing-complete computers inside Minecraft using redstone or out of physical dominoes. This proves that computation is not about silicon, it is about the logical processing of information according to a set of rules. The definition of a computer is currently expanding as we move beyond traditional silicon-based architecture. If a computer is fundamentally just a system of input, memory, processing, and output, then the materials we use to build those components can change. Figure 13 displays a futuristic render of quantum circuits and DNA computing. Quantum computers utilize subatomic particles to perform calculations in ways that would take classical computers millions of years. They aren't just faster, they represent a fundamental shift in how we process state. Similarly, biological computing uses DNA strands or living cells to act as logic gates, as shown in the biological cell animation of Figure 14. Scientists have already programmed DNA to solve mathematical mazes, suggesting a future where computers could be grown rather than manufactured. Regardless of whether the machine is made of silicon, photons, or biological cells, the core essence remains the same. The von Neumann diagram from Figure 7 reappears here as a translucent overlay on future technology, emphasizing that the blueprint drawn in 1945 is still the foundation for any mind we might build. The machine that gives you a weather report and the machine that may one day achieve true artificial consciousness share the same logical soul. This soul is not a mystery. It is a set of elegant ideas regarding the flow and transformation of information. To summarize the key takeaways of this exploration, first, a computer is defined by its structure: input, memory, processor, and output, not its physical form. Second, all computing is built on the simplest possible math, logic gates performing and, or, and not operations. Third, the concept of Turing completeness means that any computer can, in principle, do any task if programmed correctly, making it a universal machine. Finally, the future of computing lies in new materials like quantum bits and DNA, but the underlying logic remains constant. As the final shot in Figure 15 shows, when you look at a laptop or a traffic light, you are looking at an idea made physical. The story of computers is far from finished, and the next chapter involves understanding the smallest building block of this entire system, the transistor. This switch, smaller than a virus, is what allows us to manifest the abstract logic of Turing and von Neumann into the digital world we inhabit today. This concludes our walkthrough of the fundamental nature of the computer.